A database management system, or DBMS, contains information about a particular enterprise. It's a set of programs to access the data about that enterprise, and it's an environment that is both convenient and efficient to use. Regarding a GIS, attribute information is typically entered, analyzed, and reported using a database management system. Again, this is a specialized computer program for organizing and manipulating data. The DBMS stores the properties of geographic objects and the relationships among the objects. These are stored in databases. A database is a collection of interrelated data. Attribute data are an important component of spatial data in a GIS. These data may be organized in several ways, but data structures that use relational tables have become the most common method for organizing and manipulating attribute data in a GIS. A DBMS is a computer program that allows you to work with database. A database is an organized collection of data, often created or manipulated with the help of a DBMS. The database will have a specific form dictated by a DBMS, but it is not the system itself, instead just a data store. Database management systems were developed to overcome inefficiencies in the previous file and spreadsheet approaches. While these other approaches may be used for simple collections of data, DBMSs are better for applications that process large amounts of data, such as a GIS. A DBMS also allows centralized control and maintenance of important data. A single person or group may be charged with maintaining data, its currency, quality, and completeness, and with resolving contradictions or differences among the different versions of the database. Tables contain information about entities we are interested in investigating. And in the case of a GIS, this means features. Rows are individual entities, or a feature of a GIS. And columns are characteristics we want to track for each entity. Columns are also known as attributes. Attributes can be identified by a key, and they can be attributes can be identifiers, sizes, areas, colors, and other suitable characteristics used to describe the features of interest. Attributes may be simple, for example, one word or number, or they may be compound, for example, an address data item that contains a house number, a street name, a city, and a zip code. Attributes have a type and a domain that restricts the values they may take. Types define essential characteristics of an item. Common types include real numbers, integer numbers, both of various lengths, hexadecimal numbers, text fields, hyperlinks, and binary large objects or blobs. Domains define the acceptable values an item may take. For example, integers may be restricted to a domain larger than 0 but smaller than 10. Or there may be a type named color that can only take on the values red, green, blue, yellow, cyan, or magenta. We have described how spatial data in a GIS are often split into two components: the coordinate information that describes object geometry, and the attribute information that describes the non-spatial property of objects. Because these non-spatial data are frequently presented to the user in tables, they are often referred to as tabular data. Tabular data summarize the most important non-spatial characteristics of each cartographic object. For example, a table of attributes that describes counties. In this example, the attributes include the county name, its FIPS or Federal Information Processing Standard Code, population area, and population density. In a GIS, the database entities are typically roads, counties, lakes, or other types of geographic features. A specific entity, such as a specific county, is an instance of that entity. Entities are defined by a set of attributes and associated geographic data. In our example in the slide, the attributes that describe a county include the name, a FIPS code, the 1990 population in thousands of persons, area, and population density. These related data items are often organized as a row or line in a table called a record. A table then contains a collection of record, and a group of tables defines a database. Database users often demand shared access. That is, multiple users or programs may be allowed to open, view, or modify a data set simultaneously. However, if each program or user has direct file access, then multiple copies of a database may be open for modification at the same time. And we see an example of that on the top of this slide. Multiple users may try to write the data file simultaneously, and we can have unforeseen results. They may overwrite each other's work. Because of these hazards, a DBMS is designed to manage multi-user access, as we see on the bottom of the slide. The separation of data and functions into multiple levels is often referred to as multi-tiered architecture. Data are primarily stored at the lowest tier. These data may be of diverse types, including coordinate data, attribute, text, images, sound, video recordings, or other persistent data. Data sets at the lowest tier may be managed by an individual database management system. The system or programs that access the first tier at the bottom of the multi-tier system, it may also be called a transaction manager. This transaction manager typically takes requests from higher tiers and searches the relevant portions of the database to identify the requested data and perform the requested operation. The next tier in the multi-tier architecture is often referred to as the applications server. In the context of a multi-tiered database architecture, an applications server is software that passes requests from higher level tiers to the transaction manager. It converts input from above into a set of instructions the transaction manager below can understand. The uppermost tier of multi-tier architectures is typically a user interface. This tier may be a display by a single purpose or topic-specific program, such as a GIS, or a web-based interface with the primary purpose of gathering requests from the user and presenting information back to the user based on those requests. The relational model is more flexible than most other designs. The table structure does not restrict processing or queries, and the organization is simple to understand, learn, and implement relative to other database designs. It can accommodate a wide range of data types, and it is not necessary to know in advance the kind of queries, sorting, and searching that will be performed on the database. Entities are represented by rows in a table. In our forest data example, there may be a forest table with a row for each forest, and other tables representing trails, trail features, and recreational opportunities. Tables are related through keys that are one or more columns that meet certain requirements and may be used to index the rows. Keys are used to join data from one table to associated data in another table. Keys are the key to the utility and flexibility of relational databases. They allow us to mix and match data from various tables. To display data differently for different projects or audiences, we can use the keys to join the tables that are of interest to those audiences. And we can use them to allow us to organize our data in ways that help us more quickly search, select, and update our data, and to isolate our data from calling programs or changes in computer hardware. The relational algebra supports 8 primary operators: restrict, project, union, intersection, difference, product, all combinations of a given set of variables recorded in a database, join, combining tables based on matching attribute values, and divide, facilitate queries based on a condition. These operations are applied in queries to select specific records and items. These operations are depicted graphically in the slide. Restrict, also known as select, and project operations select data based on rows and columns, respectively, to provide reduced tables. Restrict is known also as a table query, and we see that below. It serves up a set of rows based on values for given variables. Project operations return a subset of columns for a table, in effect subsetting the table vertically. Product operations combine all unique values in one table with all unique values in another table to produce a larger output table. The union, intersect, and difference operations have a limitation in their application. The tables used in these 3 relational operations must be of the same kind. That means they must have the same set of variables or items or attributes or columns before they can be used in these 3 operations. A union operation combines the tables to return records found in either or both tables. The intersection operation records data that occur in both input tables and omits records found in only one of the 2 input tables. And the difference operation returns those records that are in the first table but not in the second. A join operation combines 2 tables through values found in keys. Values in one or more keys are matched across tables, and information is combined based on the matching. Selections or queries are among the most common analyses conducted on attribute data. Queries mark a subset of records in a table, often as a precursor to subsequent analyses. Queries may use and, or, and not operations, among others, use them alone or in combination. Set algebra uses operations less than, greater than, and equal to, and not equal to. Boolean algebra is what we were mentioning, uses the conditions or, and not to select features. Boolean expressions are evaluated by assigning an outcome, true or false, to each condition. Each record is inspected and is added to the selected set if it meets one to several conditions. And, or, and not may be applied alone or in combination. And operations typically decrease the number of records selected. Or operations typically increase the number of records selected. Not is the negation operation and is interpreted as meaning select those records that do not meet the following condition. In other words, the condition following the not. While database queries are typically applied to tables, we must remember that in a GIS, the tables are usually connected in some way to geographic features. Selections of table elements imply the selection of associated geographic features or elements. It's always a good idea to verify that the selection or query works as expected. Verification is often easiest by viewing the selection results either on the table, the geography, or both. Relational databases may support a structured query language known as SQL. SQL was initially developed by the IBM International Business Machines Corporation, but is supported by a number of software vendors. SQL is a non-procedural query language in that the specification of queries does not depend on the structure of the data. The language can be powerful, general, and transferable across systems, and so it has become widely adopted. Because SQL, as initially defined, has limitations for spatial data processing, many spatial operations are not easily represented in SQL. Many more selections may be specified only with complex queries, so various SQL extensions appropriate for spatial data have been developed. Joins are based on joint items or join fields. In their simplest form, a single column in one table is matched to a column in another table, and a new table created by combining rows for matched values. This slide shows a simple join between two tables. The simplest joins use a single column in each table as the matching or join item. Cardinality is a measure of how many of one entity can relate to how many of the other. 1 to n means an instance of one entity can be associated with many instances of another. For example, one department to many instructors. M to n means many instances of one entity can be associated with many instances of another. For example, one course has many students, and one student has many courses. That's an M to N, many-to-many relationship. And many-to-many relationships are resolved by creating an associative table. We usually require the source item in a join to be a primary key or candidate key capable of serving as a primary key. A column or a set of columns that uniquely identifies the rows in a table is again what a primary key is, so that there is a one-to-one or one-to-many relationship in the join. In other words, on the one side we have this primary key, so we're going to get one value, and then on the other side we can get one result, or we can get many results. We often run into problems when we attempt joins with items that have a many-to-one or many-to-many relationship. These are often considered ill-matching keys in that results from a join can be indeterminate. You can't predict the results in advance. So we create an associative table for many-to-many joins. The previous slide illustrates the most common type of join, often known as an inner join, where an output row is created only from rows that match on the join items in all of the tables involved in a join. There are other kinds of joins. For example, an outer join saves the information for non-matching rows, placing blank or null values for the items for rows that don't have a match in the target table, as in this slide. There are both left and right outer joins, depending on whether the source or target matches are in the source or target tables. Attribute tables are often huge. We have to maintain our tables by changing values, removing, adding records, or adding items to the tables. Different people and applications are interested in different subsets of attributes or columns in a table. We often break our table up into pieces, many tables, and use relational joins as needed to combine them back together. If relational tables are not carefully constructed, they can suffer from serious problems in performance, problems with consistency, we can have redundancy, and we can have excessive maintenance as a result. Data that are stored in large tables may be redundant with wasted space, and long searches may be needed to select a small set of records. Updates on large tables may be slow, and the deletion of a record may result in the unintended deletion of valuable data from the database. Smaller, more carefully constructed tables are usually more useful. Normalizing is the process in databases that helps us to correctly organize data into tables. It reduces total data storage. Changing values in the database is easier if they've been normalized, and it insulates information. It is easier to retain important data. Many operations are easier to code as a result of normalization. Keys are important in structuring relational data tables. Primary and foreign keys are often defined, which are used in joining tables. Primary keys may sometimes be concatenated or, in other words, formed from several columns, rather than just from one column. Entry and manipulation of key values is often constrained so that tables may function properly. As noted earlier, relational tables use keys to index data. There are different kinds of key. A superkey is one or more attributes that may be used to uniquely identify every row for a table. A subset of attributes of a superkey may also be a superkey, and this is called a candidate key. A primary key for indexing a table is chosen from the set of candidate keys that may be available. There may be many potential primary keys for a given table. However, it is usually the process to use only one primary key per table. The parcel ID is the primary key for the table we see in this slide because it uniquely identifies each row. A table is in first normal form when there are no repeat columns. The land records table at the bottom of this figure has been normalized by placing each owner into a separate row. This is a table in first normal form. There is a saying that you can use to explain how to get into third normal form. Every non-key attribute depends on the key, the whole key, and nothing but the key. Here in this slide we see this rule is applied to decompose our original table into several tables in third normal form. And again, the saying that we can use is every non-key attribute depends on the key, the whole key, and nothing but the key. And again, this land records table was taken from figure 825 in the text, and we see here in this slide the third normal form. Relational tables are often placed in normal forms to improve the correctness and consistency of the data, to remove redundancy, and to ease updates. Normal forms seek to break large tables into small tables that contain simple functional dependencies, as we see here. This significantly improves the maintenance and integrity of the database. Normal forms may cause some cost in the speed of access, although this is a diminishing problem as computer hardware improves. Thank you. Good evening.